Hello viewers, welcome back to the course on scientific computing using MATLAB. So, in the previous lecture we have discussed about the MATLAB code for Gauss-Seidel method. Now, we will continue from the convergence. So, today we will discuss the next lecture, that is 28. So, let us do that. From the previous lectures, that for iterative methods we are able to find what is the rate of convergence. So, iterative method I am able to find the rate of convergence, but what about the direct methods? So, direct method means what about the Gauss elimination, or what about the LU decomposition? So, can we talk about the rate of convergence of this one? So, in this case we can talk about that the complexity of the whatever we call it the algorithm, because in this case we are able to find the solution not in the form of iterative methods, but we find the solution in just in one complete process. So, that is not repeating again and again. So, that is we can say that whatever the algorithm we have written for solving the system of equation using Gauss elimination or the LU decomposition, we will find the complexity. Complexity means that, like for example, for a Gauss elimination method, we know that we have a system Ax is equal to B, and then we reduce into the upper triangular matrix. So, Ux we reduce to a new matrix. So, maybe I can call it as a B, and then we reduce this one using the elementary operation, and then using the back substitution we are able to find the solution of the given system. Now, from here in transferring from given system to the upper triangular system, we do addition, subtraction, we do multiplication, and then division. So, in computer the memory is used for doing addition and subtraction is same, and for multiplication and division is same. So, these steps addition and subtraction is treated as one, and the multiplication and division also treated as one. So, we in the abbreviation we use is addition, subtraction, this is multiplication and division. So, let us try to find the complexity of Gauss elimination method. Because this word complexity we must have heard in the data structure, the course related to the data structure or in the computer science. Wherever we are discussing any algorithm, then we discuss about the complexity. So, now I want to find what is the complexity of the Gauss elimination method. So, let us I have a n cross n matrix, and this is my system. Now, what I do is that, suppose this is my matrix A, and that is A11, A12, A13 up to A1n, A21, A22, A23 up to A2n, and AN1, AN2, AN3 up to ANn. Now, what I do is that I will go to step 1. So, in the step 1 what I want to do, I will use this as a pivot. So, this is my pivot, first pivot. So, I will use this pivot to make all this element below this 0. So, this one I want to make 0. So, what I do is that I will take the multiplier. So, that we have already discussed. So, I will call it M11 or maybe I can call it alpha. So, that multiplier will be minus A21 by A11, because I want to make this element 0, first this element 0. So, what I do, I will divide this whole row by A11 and multiply by A21 with the negative sign. And then, so after this one, so after the step 1, so let us do what will happen in the step 1. So, the first row will be same as given to us. Now, in this case what I do is, after the step number 1, in the first step I will make this 0, and then from here I can write that this element A22 in the step 1, that will become A22 plus this multiply alpha, and that is A12. Similarly, the next one will be there, and the last it will be A2n, the new element will come, that will be A1n, that will be A2n plus alpha times A1n. So, now I want to see how many number of addition and subtraction and how many multiplication and division. So, in this case, if you see from here, here I am multiplying this one by this factor. So, in this case I have done one multiplication. Now, I will ignore the steps involved to make this element 0. Now, from here you can see that in this case what I am doing, I am one multiplying and one dividing, or one multiplying and one addition. Similarly, next is one multiplying and one division, multiplication and addition. Here also one multiplication and one addition. So, from here you can see that. So, now I have to, from here, so I will change this matrix. Now, I will put the right hand side element as a last column, because whatever the operation we are applying on the matrix, that is also applying on the right hand side. So, I will again making this element B1, B2 up to Bn, and then this is my matrix. Now, this also will become B1, and B1 will be multiplying alpha B1 adding to this B2. So, that will be this one. So, now from here you can see that the dimension of this matrix is n cross n plus 1. So, that is n cross n plus 1. Now, I am not doing anything with this one. So, the remaining columns I am doing. So, I can see that the number of additioners I am putting n, and the number of multiplication is also n. So, to reduce the first element in the second row 0, I am doing n additions and n multiplication, and one multiplication I have done for this one also, because I was multiplying by this factor and then adding this one. So, here I can say that the total number of multiplication will be increased by n plus 1. So, this will be increased by 1. So, this is the n plus 1 multiplication I am doing. Okay. So, the same thing I will do again to make this element 0. So, in this case also I am multiplying this with this factor alpha. So, to make this element 0, what I am doing? I am doing this element as A31 plus alpha A11, where alpha is minus A31 by A11. So, this is my factor now. So, now in this case also I will doing the same thing, and then I am writing here A32. So, that will be A32 plus, so this multiplier we call it M31. So, I am doing this M31. So, that is alpha I am again choosing. So, this is alpha, you can choose. So, let us take this as a M only, because this alpha will be same in that case. So, I will call it M. So, this alpha is M11 and all this one. Now, this alpha I can delete and I can make it M31, and then I will put A12. So, 31, 1, 2 and so on, and in the end I will get A3n in the step 1. So, it will be A3n plus M31 A1n, and this will be again the B. So, this B, so this will be B31, and B31 I can write as B31, this will be B3 plus M31 into B1. So, that will be my B31. So, now in this case also you can see that I am doing n number of addition and n number of multiplication. Okay. So, and one is process is doing to multiply by this one. So, I can directly write n plus 1. So, the same thing is going to happen. So, this is second row, third row. So, in the last row I am going again n and n plus 1. Now, from here you can see that total number of steps involved, total number of operations, because these are the operation addition and multiplication, total number of operations involved in step 1. So, that is my step 1. So, it will be, so now this is n n n, and you can see that I am, this is the n rows. So, first row I am leaving. So, it will be n plus n minus 1 times. So, I can write that this is n minus 1. So, that is my addition or subtraction plus the n plus 1 into n minus 1 times. So, that is the multiplication or division. So, these are the total number of steps involved in step 1. Now, let us do the next one, the step 2. So, in the step 2, what is happening now? I am leaving this one. So, my matrix will be A11, A12 up to A1n, B1. This is 0, 0, 0, all are 0. Here I am getting A22, A2n, B2, right, and then A32, A3n, B31 and so on, AN2. So, this will be AN2, ANN, and this is BN. So, this is I am able to do this. Now, I will concentrate on this matrix. So, the size of this matrix, if you reduce this one, so you can see that in this case first row is gone now. So, reduced matrix, this matrix have the size n minus 1 rows into n. So, 1 it is reduced by 1. So, this is n minus 1 into n. Now, the same thing will happen again. So, from here I can see from here that the number of operation involved. So, addition, subtraction, multiplication and division. Now, from here you can see that earlier it was n number of steps, now it is, I am looking at this. So, it has n columns. So, it will be n minus 1, n minus 1 and so on, n minus 1. So, now n minus 1 addition, because now what I am doing is that I am making first this element 0 and all this element 0, and the next element will be addition and then multiplication, addition and multiplication and so on. So, in this case earlier it was n plus 1 column. So, 1 is reducing. So, I am getting n minus n. So, in this case I already have n columns and I am leaving this one. So, I will get n minus 1 column left, and then in the multiplication and division the same thing, the number of column was n plus 1. So, I am taking n plus 1. So, now from here I can see that this will be n, n and n. Now, from here I can see that the total number of operation involved in step 2. So, that will be, now see, the number of rows are same, only thing is that the number of rows is n minus 1. So, it will be n minus 2. So, it will be n minus 1, n minus 1, n minus 1, n minus 2 times, because I am starting from here, this is. So, the already number of rows by n minus 1. So, I am leaving the first one. So, it is n minus 2 into n minus 1. So, that is n minus 2 into n minus 1 plus. So, this is I am now taking n. So, n into n minus 2. So, this is total n and this is n minus 2. So, this is n minus 2 and this is my n minus 2. So, that is the total number of. So, this is my addition, subtraction and this is multiplication and division. Now, from here you can see that earlier it was n minus 1, now it is n minus 1, n minus 2, n plus 1, n minus 1, it is n minus 2. So, if you see from here, then after so it is starting from step number 1. So, after n minus 1 steps, because when I have 3 by 3 matrix. So, in the first element I have 3 by 3 matrix. So, 3 by 3 matrix, in the first step I will reduce this one zeros and the next step I will reduce this one 0 and then it will be upper triangular. So, if I have a n number of rows, then after n minus 1 step we will get upper triangular matrix that is U, and then we are able to solve this one. So, in the n minus 1 step now I want to find that So, total number of operations involved. So, I can add all this one together. So, now I can n minus 1, n minus 2 to n minus 1 and so on. So, if you see from here, I can write that summation, this one I can write as I minus 1. So, you can see from here, this is n minus 1 into n minus 2. So, this I can write I, and I is moving from to n, right. So, this is from I from 2 to n. So, this is the number of addition or subtraction, because in the last you will get only this element left. So, I is moving from 2 to n, because it is n minus 1. When I put 2, it is equal to 2 in 2 minus 1, so 2. So, only 2 addition I have to do for finding the last one. One addition for this and one addition I will do for the right hand side vector. So, this is only 2 additions we have to do in that case for the 3 by 3 matrix. So, similarly I can go from here. So, in the last I have to do 2 addition and then 2 multiplication. So, this is plus. So, this one I can do as, now you can see from here, it is n minus 2. Earlier it was n plus 1 minus n. So, whatever the element I am taking, minus 2 is coming here. So, it is n minus 2. So, from here you can see that I can write it as I plus 1, I minus 1, and I is moving from 2 to n. So, this one I can write. So, when I is equal to n, it is n plus 1 into n minus 1, then n minus 1 it will be n minus 2, so on it will keep going. From here I can write, so this is the total number of steps involved in multiplication or division. Now, from here I can write this as, now you can see that it is I from 2 to n. Then what I do is that I just transform that I is equal to k plus 1. Now, if I is 2, then the k is 1. So, if I change this one, then my factor will move from k from 1 to n minus 1, and this will be k plus 1 into k plus summation k from 1 to n minus 1. Now, k minus 1 is k, and this will be k minus 1, because I minus 1 is k. So, I minus 1 is k and I plus 1 will be k plus 1 plus 1, k plus 2. So, this is k plus 2, sorry. So, k plus 2 will come. Now, after doing this one, so from here I can get that this is equal to k from 1 to n minus 1. So, this would be k square plus k plus this is k from 1 to n minus 1, this will be k square plus 2k. So, now from here you can see that now I know the summation from, so this is already known to me, that summation n, so that is n into n plus 1 by 2. So, that we already know the summation, and summation n square is equal to n plus 1 2n plus 1 by 6. So, it is up to n. Okay. So, now from here I can write that this will become summation. So, first I am doing this one. So, it is k from 1 to n minus 1 k square plus summation k from 1 to n minus 1 k. So, this will become this summation will become k square. So, it is n minus 1 plus 1 and 2 n minus 1 plus 1 by 6 plus this one will be n minus 1 into n minus 1 plus 1 by 2. Now, from here I will get this will become, this will cancel, this will cancel. So, it will be n minus 1 and then into 2n minus 1 by 6 plus n minus 1 by 2. So, from here I can write this as, similarly I can write from here, and now after doing this one you will see that I will write this as, so this can be written as, if you take the n, so it is n square minus n 2n minus 1 by 6 plus, so I can take the LCM, so it will be n square minus n by 2. So, I can take the LCM common, so it will be 3, and now I can write from inside. So, this will be 2n square minus n square minus 2n square plus n. This one I can write plus, it is 2. So, this will 2 will come plus, now it will be 3 n square minus n, so by 6. Now, from here, so this is n cube, right, yeah. Now, it is 2n cube. So, from here I can write that this is 4n cube and this will be minus 6n square plus 2n plus 3n square minus 3n by 6. And now, from here the same thing I can do for this factor also, though almost the same thing will come except the 2 is there, otherwise the same form will come. Now, if I get this type of value, now you can see that if n is large, implies that n cube will be the dominating term, because if n is, suppose in this case also if I put n is equal to 5, so then this will be the dominating term. It may happen that this will be cancelled out and this will dominate, but one thing is true, that if n is large enough, then definitely these terms n cube will be the dominating term. So, that is true, that in that case this n cube will be the dominating term. So, from here I can see that I can write that the total number of operation in this case is approximately of order 2 by 3 n cube, plus also coming from here. So, that is also in the terms of n cube plus something. So, I will just take this plus order of n cube into some factor is there. Now, from here I can see that, from here I can say that the Gauss elimination method, from here I can say that the Gauss elimination method, the complexity of Gauss elimination is order of n cube or 2 by n, 3 n cube. It is same as n cube, does not matter, I can write as a order of n cube. So, that means that suppose I have maybe n is equal to 10. So, if I take n is equal to 10 matrix, 10 by 10 matrix, then the number of operations we have to do is 10 is to power 3. So, and if n is large enough, so 10 is to power 3 means 1000 operation we have to do, and if n is maybe 1000, then you can see that the number of operation will be 1000 power 3. So, you can see that how many operations we have to do, 10 is to power 9 it will go. So, in that case we have to do so many of operations to solve this type of system. So, in this case I can say that this method is very expensive. Because the number of operation, and this factor I just want to define what is the meaning of O. This is a big O. So, if I write big O of n cube, it means if I put limit n tends to infinity, so I can say that some function f n is of order n cube, that implies that the limit n tends to infinity. So, n cube so if I say that, then I can say that the f n over n cube is constant. So, that is the meaning of order of n cube. So, if a function of n is the order of n cube, means it means that f n divided by n cube, that will be a constant value. So, that is the meaning of big O, and it is used in the complexity. So, that is the complexity of the Gauss elimination method. So, now we will stop here. So, today we have discussed the complexity of the Gauss elimination method, and we found that this complexity is n cube, and that is very expensive, because when we increase the size of a matrix, then the number of operation will go n raised to power cube, and it will increase very fast. So, that is why we say that the Gauss elimination method is quite expensive. So, today I hope that you have learned that how we can find the complexity of the direct methods, and also we have discussed that rate of convergence for the iterative method. So, in the next lecture we will continue for this one. Thanks for viewing this lecture. Thanks very much.